Hey, and happy college acceptance day. Fire up chips. What we're going to be looking at are the various parent functions that are the core of making graphs using transformations. So let's get started. Our first graph is the linear, f of x equals good old x. It's basically a line with a slope of 1. The key point that we need to worry about is that intercept through the origin 0, 0. Now, as you can see, the domain and the range are both all reals because any number can be plugged in for x, and thus any number can come back out again. Next up are quadratics. F of x equals x squared. In this case, the key point on our graph is going to be that vertex, the bottom of the parabola. And in the parent function, the vertex is located at 0, 0, the origin. For these graphs, the domain represents all reals. Any real number can be plugged in for x. The range, however, represents all the values greater than or equal to 0, since our parabola is only in the positive range. Similar to quadratic are the cubic functions. F of x equals x cubed. This graph follows a bit of a swoop. Goes up, levels out, and then picks up again. That point where it levels off is referred to as the inflection point. It's like the vertex of a cubic, and in the basic parent function, it's located at 0, 0. The domain represents all real numbers. Any number can be taken to the third power, and the range is also all reals. Any number could come back out again. Related to quadratics is the square root function. F of x equals the square root of x. As you can see, it's like a parabola laying down on its side. Because we're focused on the function, we only draw the upper half of that parabola. The key point, then, is what would have been the vertex, and is now the jumping off point. The domain, thus, is limited to x is greater than or equal to 0. Likewise, the range, or our output values, are also only greater than or equal to 0. Exponential functions can be written in the form f of x equals some number to the x power. Since we're taking it to a power, that changes our outputs. There are two key things to think about on these graphs. The asymptote, which represents the line that we never reach going down as we go into the negative x range, and the intercept, which by default happens at 1 regardless of what a is. For these graphs, the domain represents all real numbers. Any real number can be substituted for x. However, the range is limited only to numbers greater than 0. No matter how large of a negative number I plug in for x, this graph will never actually touch the asymptote of y equals 0, and thus y equals 0 is not in my range. The range, thus, is only y greater than 0. Logarithmic functions are the inverse of exponential functions. F of x equals log base a of x, where a can be any number. For these, they look like the exponential function flipped around the line y equals x, or starting down at a very large, very negative y value, and then continuing up on a curve. The important parts of this graph include the asymptote, which in this case is now x equals 0, and the intercept, which is again at 1, although in this case it's at x equals 1. For these, my domain represents all numbers greater than 0. Like the exponential function, 0 is not included because it's on the asymptote. The range would be all real numbers. Our final parent is the absolute value function. F of x equals the absolute value of x. This graph looks like a V, a line going down to the origin and then going back up again with a slope of 1. The key point on this graph is that turning point at the origin 0, 0, where our negative numbers flip and become positive again. For this graph, the domain represents all real numbers. Any number can be plugged in, but my range is limited only to numbers greater than or equal to 0. This is because the absolute value, recall, strips the sign off of the value and returns only positive answers. 0 can still be used and thus returns 0. When we make our graphs, we're going to be using these parent functions as our basis, so it's very important that you know what each of them looks like, including their key points. For most of our transformed graphs, what we're going to do first is draw the parent function, note its key points, and then apply the transformation rules that we've written to that and draw our new graph. So I would recommend going back to this one more time if you have to. Make sure that your notes adequately reflect all of the major ideas for each of these functions.